Okay, let's talk about the combined gas law. And that's an equation where more than two things are changing. You have a before and after equation, and you have more than two things. So the equation you use is P1 V1 over N1 T1 equals P2 V2 over N2 T2. And we'll see in class that we derive that by using the ideal gas law equation. And we kind of set both sides equal to R, and you'll see that it's just what changes on the left and changes on the right kind of work out. So let's take a look at the equation here. So what we have here is it's a doozy. You let your 22.4 liter balloon, that's V1. I like to make a chart so I don't go crazy. At temperature 23 degrees Celsius, let's change that to Kelvin, 298, which is 23 plus 273. And 1 atmosphere pressure, 1 atmosphere, P1, and let it go. Oh, they don't tell you how much moles. Interesting. It floats to the stratosphere where the air pressure is P2, 0.02 atmospheres, and the temperature is 270 Kelvin. Oh, that's nice. They changed it for you. What will the new volume be? So we have three things that are changing, but it's the balloon. It started out like a balloon, and it's going to change size, but we're not letting any of the particles out. So the number of moles before and after is the same. So what we do is we set up the equation, P1 V1 over N1 T1, P2 V2 over N2 T2, and you cross off the things that don't change, which is N1 over N2, okay? Then you just plug in your numbers like before. P1 goes here, V1, right, over T1, P2, V2 over T2. And to solve for V2, if you want a little, it's the same thing, cross multiply and divide this times this divided by this times this, really. It's, algebra. So this times this, and divided by this times that. So there it is. So just equals V2. Atmospheres cancel, liters cancel, Kelvin cancel, and you're left with liters. This is how you know you set it up right. If you flipped it, it wouldn't cancel properly. So it's really important to have your units so you can catch yourself. This times this times this, divided by this times this. I recommend putting them in parentheses in your calculator. Okay, and then this divided by that is 1,015 liters, which is amazing. So the balloon, as it goes up into space, it's cooling down, so it's getting smaller, but there's less atmospheric pressure on the outside, so it gets larger, and it gets to about 1,015. And I had some students from another school that created a space balloon. They put on cameras, and they actually showed the balloon getting really large, and it burst once it hit the stratosphere because it hit its max. But they're designed to expand, which is pretty freaking cool. What if you take the same balloon to the bottom of the sea with a pressure of 404 atmospheres? That's the bottom of the Pacific Ocean. Hopefully you never end up there, or if you do, you're in a submarine. And a temperature of 4 degrees Celsius, also known as 4 degrees plus 273, which is whatever that is, 277. What will its new volume be? So they're giving you everything except for V2. So it's the same equation as last time. We plug in P1 V1 over T1 equals P2 V2 over T2. Notice how I kicked out the ends because we know that those aren't changing. So there's our P1, our P1 V1 and our T1. I keep on flipping them. P2 V2 over T2. To solve it, this times this, and then bring this down here. Boop, 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 boop. Liters cancel. Liters stay the same. Kelvin cancels, atmospheres cancel, and you're left with liters. And multiply this, divided by this, 0.052 liters. So look how tiny it gets at the bottom of the sea. So don't take your balloon friends to the bottom of the sea.